Welcome to the McIlvaine Hot Topic Hour this morning on combustion optimization using coal and airflow measurement. And we're very fortunate to have Dave Earley as our presenter today. So I'm going to turn the microphone over to him, so to speak. But we are going to need everybody to get their phone on mute. So that will be something that you'll want to do. And then when you want to ask a question, you just come in with us there. So there are some phones I'm hearing in the background there, some talking. So if we can get those on mute, appreciate it. And Dave, I'm going to let you start rolling here. If we have to, then we'll switch and put everybody else on mute. But why don't you present the material? But first, give us a little bit of your curriculum vitae, if you would, please.
Sure. Yeah, this is Dave Earley with Combustion Technologies Corporation. We run the combustion optimization side of Air Monitor's business. Air Monitor's been around since the 1970s, and the power industry has become one of their largest businesses, and so they've sort of separated into AMC Power. And we'll be presenting their coal and airflow measurement systems as used for combustion optimization. I've been associated with Air Monitor for about 20 years now, either directly with them or with Combustion Technologies. And we've been doing combustion optimization for about the last 10 years, since coal flow measurement came into being. The reason people are getting involved in combustion optimization are various. A lot of utilities use this for different reasons. Some people use some of the products like overfire air measurement just as a NOx reduction tool. Some people are using complete air and fuel optimization systems to reduce CO, to reduce NOx, to reduce unburned carbon. Lately, there's been a lot of fuel flexibility issues, people wanting to burn coals that don't burn well in their furnaces, so they're using equipment like ours to help them burn better without CO and flagging problems. The water wall corrosion and downtime is another issue that comes into being with that as well. The coal flow technology is probably the newest thing that we have, and I say new to the power industry, is 10 years. We've had this out almost a full 10 years. We re-engineered it to what we call PfFLO 3 about 7 years ago, where we took the technology that originally came from Germany. We licensed it, we re-engineered it with some of our customers in mind, and have come out with it again as PfFLO 3. It's a microwave technology for measuring mass, and we use cross-correlation for measuring speed of fuel. And when you multiply the mass by the speed, you get mass flow. The technology isn't really new. Again, 10 years old in the power industry probably still considers it new. But we've been doing combustion optimization using this product now for many years, getting CO reduction, NOx reduction, unburned carbon, and more. What we now know is that we can adjust coal between pipes using coal valves, and I act like that's a big deal, but it is, because two-phase flow, the solids being the solids being the coal phase and air being the gas phase, adjusting it with valves or variable orifices is tricky, because when you adjust a valve, you're taking and making changes to the dense phase and the gas phase. So when you make these changes, you need to look at the fuel speed in addition to the coal mass to make sure that you're doing it without creating layout. The other thing that's very easy to do with coal flow measurement is all low NOx burners, which most people have low NOx burners today, have the ability to regulate how much secondary air goes to the burner, either a moving sleeve or a disc. But most of the OEMs don't give any indication of, well, how much air should go to that burner. If we measure the coal to each burner and we measure the air to each burner, we can very accurately dial in an air-to-fuel ratio in each burner. So that's something we're doing a lot of now. Primary airflow also has to be adjusted to accommodate the heaviest burner. If an operator has problems with potential pluggage, he's going to increase his primary air. Meanwhile, the other burners, which may be light, you're going to be blowing your coal right through your flame. You're going to have elevated superheat and reheat temperatures, high unburned carbon, and so on. The other thing that we find is that the primary air, even though we can measure it very accurately using airflow equipment like ours, how much primary air you need really can't be determined until you look at the fuel particles as they move to the burner. So we're going to go through some of this. Most of this presentation is going to go into data where we have used the equipment. Again, this is a boiler. I'm sure everybody here knows what this looks like. On the right where I show CEM, this is just pointing out that Air Monitor has been involved in SEM's flow measurement. We also do primary airflow measurement, secondary airflow measurement, overfire air measurement, IBAM, which is individual burner airflow measurement, and now PfFLO. The reason for the boiler schematic, over on the right where the CEM is, you all know that we measure O2, you measure O2 on your boilers, and you control how much air goes to this boiler through that excess O2 measurement. And typically you're in the high 2.6, 2.8% excess O2, which is 20-some-odd% extra air to this furnace. And in the good old days, all that extra air went into the combustion zone right here in the wind box. But overfire air is a tool that's been used more in the last 15 years for reducing NOx. Overfire air runs about 20-25%. And if we leave our O2 measurement where it was, at 2.5 to 3%, all that extra air that we had in the combustion zone is now being run up here to the overfire air zone. So if we have a rich burner or a lean burner running down in this area, it's not as likely to be forgiven. With all the extra air years ago down here, if we had a burner running substoichiometrically, extra air could be delivered to it. Now if it's substoichiometric, you're going to be making CO, you're going to be making unburned carbon, and you're going to be trashing your water walls. So individual burner air and fuel flow measurement has become much bigger since the advent of overfire airflow systems. The pulverized coal flow technology that we use is not a single technology, it's two technologies. We use microwave to measure the mass of the coal, and we use electrostatic cross-correlation to measure the speed of the coal in the pipe. Typically we use two sensors as shown here on the bottom left, a transmitter and a receiver. On the right they show up as this is the transmitter and this is the receiver, the up and downstream sensor. The picture on the right I've chosen to show a third sensor, and I'll explain that. The microwave measurement is simply a change in frequency. The only calibration that needs to be done to measure coal in a coal pipe is to look at this frequency spectrum when the pipe is empty, and we're going to develop this baseline or zero frequency curve. When we load the pipe with coal, the frequency shifts, and that frequency shift is dependent on the mass of what's between those two antennas, those two sensors. So that's our mass measurement. And I just want to highlight that that mass measurement is very critical that we establish this baseline zero. So we want to make sure we get that zero and that we check that zero every time a pulverizer is out. What we do with the same two antennas is we look at a fingerprint of the coal particles electrostatically as they move past this sensor and this sensor. And we mathematically cross-correlate them. So when we can know when the material that was, or the bulk of the material that was here is now here. And we simply note the change in time. The distance is the spacing between the sensors, the change in time being how long it took for to see the comparison. Distance over time is speed. So we very accurately know the speed. Through the course of this hour presentation, I'm also going to talk about how important that speed is to combustion optimization. It is equally as important as the mass flow of coal moving through a pipe. Now, the reason for the third sensor, in some cases, these sensors from a mass flow standpoint have to be 1.5 diameters apart from a microwave standpoint to measure this mass. If we were in a 12-inch diameter pipe, that would be 18-inch spacing. Now we're trying to cross-correlate something across 18 inches, which is very doable. As we get into a 24-inch diameter pipe, now we've got 3 feet of spacing between those antennas. The cloud of coal dust changes too much across that 3 feet, and so cross-correlation isn't that simple. So in large diameter pipes, we use a third antenna, so that the upstream 2 antennas are measuring the mass of coal, and the downstream 2, these 2 here, are measuring the speed of the coal. Again, this is an example of velocity. This screen, I'm going to show you several screens throughout the course of this presentation. Some will be the mass flow of coal, and some will be the speed or velocity of the coal. This is a typical velocity screen as presented by our equipment. And if we were to look at our mass flow screen at this point in time, this is the fuel velocity, the mass flow would drop to 0 because this plant shut the feeder off. So now we're still measuring velocity because there's still movement in the pipe, but now what we're cross-correlating is the dust that remains from the air preheater. And this is an important screen because what this screen depicts is that without a change in primary air, tracking the fuel velocity, we see a much lower velocity, 60 to 80 feet per second. But the air velocity in a coal pipe is much higher. The difference between these two is the slip. Coal particles will always move slower than air. They have to. It's the friction between them that carries them to the burner. How much slower depends on the fineness of the coal, the moisture content, piping runs, and so forth. But this also tells us why manual sampling is not an accurate way to measure flow, because manual sampling tells you to first measure the speed of the air and then extract your coal at that speed. Well, the air speed and the coal speed are very different, so you can't infer one from the other. The other reason I like to show this screen is that while we were doing this particular project, the reason they shut the feeder off is somebody wanted to do a clean air test. So the Pitot tube test was done in each of the coal pipes with the feeder off, and our air velocities were within 1 to 4 feet per second of the measured clean air test. Another question that typically comes up when we're presenting this material is, are the antennas or sensors, as you call them, are they going to erode over time? We've not had any erosion issues other than with Texas lignite. And this is typical of what we see with these sensors here. This top antenna came out after 4.5 years of service, and there's no measurable wear on it. The sensor is a tungsten carbide sleeve over a copper wire being the antenna. The sensors are connected to a transmitter, which is located in the field, usually up on the burner deck somewhere. And that transmitter does all the work. So we're doing the conversion of the frequency curve shift to a mass flow, or to a mass, and the cross-correlation to a speed, all done in the field, and then we transmit those via 4 to 20 or digital back to the DCS and to our SCADA computer. Again, the SCADA being what is showing curves like this. Typically, the transmitters could be located separately along the burner deck or anywhere in the plant, and then the 4 to 20 sent back to the DCS. Or if the digital signal is used, all the transmitters can be daisy chained together, and then a home run Cat5 cable can be run back to the control room. In practice, the utilities have seem to have decided to I seem to have locked up. If you can bear with me.
Yeah.
While you're getting back in there, Dave, what about the variations in coal where you might be blending coal? Is this a problem?
It could, you know, Bob, the much like on a feeder, if you're going to run coal on, if you're going to run different coal in different pulverizers, they would be slightly different in terms of how the mass measurement. You need more mass of a coal with a lower BTU content than you do a higher BTU content. So you'd have to be aware of that when you. There we go. Are we back?
Yeah, we're back looking at your desktop.
Good morning to you.
More typically, what power plants prefer to do is to put all our electronics in a common enclosure, either if it's a T-fired unit, say an enclosure per corner, or in a wall-fired unit.
We're getting some feedback here. Let me just make sure the guys get on there.
That right. Did you break the 70 or
somebody on the phone there needs to get their phone on mute. We're getting we're getting some feedback there. We need a gentleman to get his phone on mute.
That's better.
Okay, fire away.
So again, typically the enclosures might be, or the electronics might be ganged together. What you're looking at here is an enclosure that is measuring 10 burners.
I think, Dave, what I'm going to do is put you, let's get you so you don't have any more problems here, I'm going to go back and let's see if we can get the participants on mute here, and find who that is that's talking. Yeah, just keep talking away. And
this particular screen I like to show because it shows the importance of both mass flow measurement and velocity measurement. The top screen is the mass flow of 4 burners out of an MBF pulverizer. And you can see the distribution from the green pipe down to the blue pipe. On the lower screen, we're looking at the speed of the particles as they move through the coal conduit. And you can see these are over 100 feet per second. Now, primary air curves and how much primary air can be debated, you know, back and forth, how much you need for what fuel type, but I can assure you that 100 feet per second is not desirable. And in a case like this, you're going to blow this coal right through the flame. You're going to have high superheat, reheat temperatures. You're going to see a cloudy furnace. It's not going to be very pretty, and that's exactly what this particular power plant had. It had a slagging furnace. When you opened observation doors, you couldn't even see flames. It was so smoky. When we walked into the control room, we saw the high velocity. We asked the operator to decrease the primary air, and at this point you can see that the velocity of the coal particles decreased with the decreasing primary air. What also happened at that time, with the new dynamic in the mill of a different PA to feeder curve, is the coal distribution change. Now, this is not normal, but whenever you change something, it can have an effect on your coal distribution. And in this case, it improved our coal distribution without even needing to put in coal valves or anything like that. So through the use of primary air optimization and seeing how it affected the coal distribution and coal speed, we were able to solve a slagging problem on a Powder River Basin furnace. This is another 4-coal pipe pulverizer. This time we're looking at the coal mass flow output from the air monitor SCADA system. So our data acquisition system here is showing a 24-hour window of data. And the blue pipe, the green pipe, and the red pipe are what we call normal operation. And the yellow pipe is erratic. The data is always somewhat erratic. Coal flow in a coal pipe is not like water coming out of a garden hose at 45 pounds pressure. Coal particles moving in a coal pipe at, say, 10 to 12 inches of water are going to be bouncing around. It's a very erratic process. While we could filter some of that out, we choose not to. We want to look at those raw signals. It tells us a lot about how the fuel is being delivered, how smoothly that fuel is being delivered to the burner. And in this case, we can see the yellow pipe, which is heavily loaded, is not very smooth. It's what we call slugging. You've got coal laying out and blowing and laying out and blowing. And again, this is a 24-hour window, so you're seeing it through a variety of mill load changes. Now, again, we measure, to get to that mass flow measurement, we measure mass, what we call density, because it's the mass of coal between the two sensors, mass per volume of pipe, and the speed. What you see here is those measurements over the same 24 hours. The top screen is the mass of coal, and the bottom screen is the velocity of coal. And going back to our coal slip issue, this is a real telling screen because we see that the milling system is throwing much more coal to the yellow pipe than the other pipes. And with the same amount of transport air, what's going to happen? The particles are going to move much slower. And if we get much lower than where we see there, that's 70 to 75 feet per second, we get much lower than that, you'll see the data get extremely erratic, and you'll plug the pipe, and this particular plant is prone to fires. When we talk about the accuracy of the device, we're measuring coal mass flow real time, every second. So if we sum the 4 pipes of this pulverizer over this 24-hour period, the top screen is the sum, the bottom screen is the gravimetric feeder. So basically every blip that feeder goes through, you're going to sense with the coal flow signals. So the accuracy is certain. Now what do? So we have coal flow, we measure coal flow. 10 years ago, we didn't know what to do. We didn't know the first time we measured coal. How do we deal with this? This is a coal valve that is easily inserted into a pipe. You don't actually even need to remove any section of pipe to install it. It's a diffusing butterfly valve. So this is in the fully open position. If you turn 90 degrees, that blade would be in the fully closed position, which would be blocking off about 60% of the cross-sectional area. The more that you use the valve, the more it actually breaks up ropes and evenly distributes fuel through the holes in the pipe. Now, we also have learned over the last 10 years where valves should be located. If you put a coal valve very far downstream in a milling system or a pulverized coal delivery system, the milling system might continue to deliver coal to that pipe, and all you're going to do is take away transport air for this depiction here, and you're going to create coal layout. If you use coal valves close to the pulverizer, they are better at creating a back pressure internal to the mill and preventing some of the coal from ever getting to this pipe. Now realize that as you close that valve, you will also take away transport air, so you will slow down the coal that's in the pipe. This is a coal valve on a very simple, the simplest system is a two-pipe system. This is one end of a double-ended ball mill. And so we have two pipes. We have the pipe in the near ground here and the pipe in the far ground here. This was a heavily loaded pipe, so the valve is closed. Here's the data from that move. So this is a mass flow screen. We close down on the yellow pipe, and the coal goes to the red pipe. I want to stress again that each measurement is individual and independent. We don't compare signals. There's no relative relationship between the two. We're measuring the mass and the speed in each pipe, and all we're doing is comparing it. So the yellow pipe's mass is decreased, and the mass shows up in the red pipe, so we know we did our job. If I were to show you the velocity screen, which I didn't include in this presentation, the velocity in the yellow pipe is also going to decrease, and in the red, probably increase. Now, how much is it going to decrease or increase? Well, it depends on how much it has to do less work, because there's less mass of coal in the pipe. So often there's not much of a velocity change, but if the milling system continues to deliver coal to the heavy pipe and you continue to close your valve, you will create low velocities. So care has to be taken to look at both the mass flow and the speed. This is a much more complex system that we're looking at here. This is a 9-pipe MPS mill outlet, and you can see the coal valves here are right on top of the isolation valves, the burner isolation valves, as close to the mill as we could get to make them effective. And this is the typical data. So we went from 9 pipes with a distribution on the left to 9 pipes with the distribution on the right. And one of the natural questions might be, hey, how come we didn't try to get more coal off the green pipe? Well, I'm sure the plant did try to get more coal off the green pipe, but by closing the valve too much, the velocity probably got too low, and they decided, well, this is more acceptable. This is where we will leave it. And so this was the distribution that they ended at. This is another case of a 7-pipe MPS pulverizer, where by balancing pipes on all the pulverizers, we were able to reduce NOx. Again, if we were to mathematically look at this data, just wanting to point out again how absolute measurement, true mass flow measurement is important. If we sum the pipes on the left of the line before we balance, we get a total mass, and if we sum on the right, we get the same total mass. We did not create nor destroy matter. We are measuring coal flow. Coal valves have been developed specifically for T-fired units that use, or some wall-fired units, I guess, as well, that use Riffles. And in this case, you can see that on the outlet of this particular Riffle, they typically use fixed orifices here. We can replace that fixed orifice with this adjustable orifice. Or in a case like this, where pressure drop was a very big concern to the plant, they didn't want to introduce any more pressure drop. They were primary or limited. We eliminated the Riffle that was in this Riffle housing, and we put in this new Riffle door with valves built into it. And this is the data from balancing using that device. So there's multiple means of balancing coal on exhauster mills and pressurized mills. This was another exhauster mill application where we detected a plugged pipe. We could see that the white pipe, there was no coal moving through it, or just a breath of coal every so often moving through it. We used the isolation valve from the mating pipe, the brown pipe, and we closed it, forcing everything through the pipe that was partially plugged until we got flow back through it. So again, using coal flow measurement, we could determine that we had a plugged pipe, and then we took corrective actions to fix that plugged pipe. This is more T-fired coal data. This was generated by one of our customers who is very happy that they have some of the best steam temperature distribution they've ever had because they balance flow to their corners. This is the mass flow of coal as summed up to each of the 8 corners on the pulverizer. And that's the as completed version. So we were able to improve corner-to-corner coal distribution on this T-fired unit, and thus improve steam temperature distribution. Coal flow measurement can also be used for troubleshooting. This is at a power plant that had what they called puffing. Periodically, they would get a high-pressure signal in their pulverizer, followed by a CO spike on the back end of the board, in the stack. And we could see as soon as we turned on coal flow measurement that there are times when all 3 pipes from this pulverizer, it's a 3-pipe EL mill, surged. And one day we were in the control room, and the operator said, well, you know, we just had a puff, and we were able to bring our cursor over to the exact instant that they said they had a puff, and we see all 3 pipes spike. What we then did for them is to follow what they normally do, what an operator does when they have these puffs. And we can see that the operator, whatever the operator was doing, when these puffs started to happen, they became very frequent. And we could see on the bottom screen that the coal velocities were increasing all this time. So the operator, when they started to have puffs, felt that adding more primary air would help solve the problem. The reality was it was making it worse. So we asked the operator, whatever you're doing, do the opposite. And so they decreased the primary air, which we can see in the bottom right. The velocity in the coal pipes decreases, and the surging or puffing, it was abated. We still don't know exactly what caused the problem, but we knew what was certainly making it worse and how to prevent it. I like to say, can you tell which pipe's on fire? This is a case none of us wants to see in a power plant, but I'm sure most of us have seen. And this particular coal pipe is ablaze. If we look just upstream at this in this same pipe, this is just upstream of the burner. We can see the paint chipping off. The fire is all in this pipe. It probably started down here in this horizontal section of pipe. If we look at the data from this, this particular plant has the option to have what's called a PA kicker. And a PA kicker means they're continuously monitoring coal and coal mass and coal speed. If any coal velocity in any pipe gets below a set point, the primary air is automatically increased to try to prevent layout. That feature was not turned on in this particular power plant. And we can see what happened. When this mill was brought back into service, there was a slug of coal that went to the pipe that had a fire. And if we look at the velocity screen, we can see that the velocity was well below minimum transport velocity. You know, at below 50 feet per second, you're not going to transport fuel. You're just throwing it into that pipe, and it's going to sit there. And so what happened was they were filling the pipe with coal, and it eventually caught fire. By going backward in history, we could see before the mill came out, normally they purge the pipes. And as I showed before, very early in this presentation, what you should do when you shut a mill off is to leave the primary air running and sweep that mill and the pipes clean. And you can always tell that's done because if you look at the velocity, those velocities would increase before the mill ultimately came offline. The mass flows would be decreasing and the velocity would be increasing. And in this case, we can see that this mill actually tripped. There was no purge in the lines, and any coal that was moving through the coal pipe settled out. We combined that with the slug of coal that was delivered, and there just was too much coal in pipe 32R, and it caused a fire. We've seen this at many utilities, going back in data, and we never want to see it. We hope that our equipment is being used to prevent fires. And here's how we can do that. This is a power plant that has a 4-pipe milling system, and Air Monitor actually got a call in the middle of the night saying, we just bought equipment from you, we put it online, but we're really not using it yet. We're just trending it. and we plugged a mill. Can you tell us what happened? And some plants allow us to dial in, so we remotely dialed in, and we could see that 2 pipes were plugging over several hours, the red and the yellow. And eventually, as they plug, there's nowhere else for the coal to go. It bogs down in the mill plugs, and we tripped the mill. But what's more telling is the velocity screen. Throughout the course of that night, and this can be a classic case of wet coal, the velocity of the coal particles is slowing down. And eventually we get to where those particles will no longer move and they start to pile up, as we see in the red and the yellow pipe. So once the operator knew this, when it started to happen on another day, the operator chose to increase the primary air manually. So we saw again some coal settling out in his red pipe and the yellow pipe. So we increased his primary air, and you can see right around here the coal particle velocities start to increase from their low of right here where my cursor is. So 2 things. The power plant decided to have engineering redo its PA curves. By looking at the fuel flow through the entire load range, they could determine when this was causing, when the velocities were getting low, to redo it so that they would have more stable coal velocities throughout the entire load range. But even the event of wet coal or bad fineness because the mill getting worn, they wanted to build a new control room screen, and I realize this is a little fuzzy. But what this screen shows is the comparison of the 4 pipes of a milling system. And in each coal pipe, we're looking at the mass flow and the speed of the coal. And over here on the left is our control block. And in this control block, what we do is we're comparing the coal velocities of each of the 4 pipes. And right now, the process variable is saying our lowest velocity is 75 feet per second. Below that is the set point. And the set point says, if we get below this set point, and this particular plant, it's programmable, this particular operator wants to use 65 feet per second. If any pipe goes to 65 feet per second, this is the control. A primary air kicker is introduced so that the primary air on this mill will be increased by this amount. And again, it's programmable. They use 5%. In the event that this happens, up here, whichever mill happened to get this PA kicker will flash, letting the operator know, I've got a primary kicker on a mill. The operator can click on that mill button, and then it will take him back to the data, so we can see exactly what caused the control system to put in a primary air kicker. In addition to coal mass flow and coal speed, one of the other things we've been working on for several years is coal fineness monitoring. And what we know from years and years of measuring combustion airflow, and now with our new experience with coal flow measurement and 2-phase flow, we've learned a lot about the relationship between the air and the fuel. We know the coal particles will always move slower than the air in a coal pipe, and we also know that the coal size, the coal particle size, is one major factor in that slip factor. So our challenge was to turn that slip, the speed difference between the fuel and the air, into a coal fineness measurement. So this device is used, this is actually one that's being installed on an exhauster mill, a double-ended exhauster mill. And rather than in each of the individual pipes, this is in the main pipe coming off the pulverizer before it riffles to multiple pipes. So what we're doing in this section of duct is the venturi. It's a very slight beta angle venturi, and it's an AR material so that we're not going to have a lot of wear. We're measuring the velocity of the air, and this was pre-calibrated in a wind tunnel so that we know that the DP through this venturi, we know exactly what the velocity of air associated with that is. We also install some of our sensors, our PfFLO sensors, but we're only measuring the speed. So here we're measuring the speed of the coal particles, and here we're measuring the speed of the air. The difference between them is our slip. And by trending this, we installed this on a plant that has an adjustable classifier so that we could control the fineness. We see the relationship between percent passing through a 200 mesh. We did it for all meshes, but here I'm just showing you the 200, and the coal slip. And by doing this time and again, we realized that there's a linear relationship. So we're now fineness monitoring, which is going to be through coal slip. This is burner airflow measurement that I want to talk about now. This is a depiction of a generic low NOx burner, and in orange are our pitot tubes that are used to measure airflow. And I'll talk very briefly about airflow measurement in general. I'm sure you all are aware how pitot tubes work. You measure a differential pressure, and you can convert that into air velocity, which can be converted into flow. This is a standard pitot tube. Standard pitot tubes aren't used very often in the power industry because they become very erroneous in the event that you have angular flow. And why do you have angular flow? Because you don't have a lot of straight duct or pipe run. So we see that for even a little bit of angular flow, your error on a standard pitot tube becomes dramatic. More common in the power industry is an S-type pitot tube. An S-type pitot tube has a unique feature in that its error is always high. It's always a positive error. So again, as you get into angular flows, you get into very large errors associated with them. And these are the angular flows, and this is the error. The error is always positive. You don't have a negative error. The danger in using S-pitot tubes or a derivative of an S-pitot tube is that you'll think you have more air moving through your duct than you do because, again, the error is positive. The air monitor pitot tubes that we use for flow measurement in primary, secondary, and overfire air ducts are based upon a Pitot-Beckheimer technology that was patented back in the late 70s. This technology is very forgiving in terms of angular flows, meaning it's still accurate even in the event of some pitch or yaw, and it's an averaging pitot tube, so that's also compensating for stratification associated with short duct runs. Again, I'm just pointing out the multiple holes on each pitot tube. But when we get into a burner, I mean, regardless of the technology, whether it's an air monitor technology, whether you're using an orifice plate, or whether you're using a thermal anemometer, there are always straight runs associated. You cannot put measurement devices just anywhere, and these are the air monitor straight run requirements for a volume probe. So the challenge, again, for a burner is how do we measure airflow in a burner when there's not even one duct diameter? So what air monitor, and this is a schematic of a burner, and where we might put our pitot tubes in this burner. Not only is it a short duct run, we've also got swirlers in there. We're trying to create swirl, which adversely affects pitot tube measurement. So the challenge was to develop a flow measurement. So air monitor uses a variation on its VoluPro pitot tube, and we've put pretty much every low NOx burner on the market in our wind tunnel back in Santa Rosa, California, and we've developed flow measurement accurate to within 2 to 3% for every burner type out there. So that you can see that unlike a normal, earlier in this, a few slides ago, I showed that your velocity is equal to the square root of a velocity pressure over density, very simple formula. When you get into flow measurement in a low NOx burner, it's a very complex formula that we end up using that becomes a function of the damper position. We need to know what the flow is. You don't just need the DP. You need to know where the damper is. So you need the feedback signal from the damper drive. And you also need to know the swirl angle on the burner, which is, they're typically fixed and set. But all that is put in the DCS so that we continuously monitor the airflow to each burner. And again, I have trying to advance my slide, a slight problem. We're going to back on in 30 seconds.
A lot of good information that we're getting here. How are you working with the end user customers to help them accomplish all this? Is it some sort of a long-term contractual basis? How does it all work?
That's a good point, Bob. Typically, when people are putting in, say, a primary airflow measurement, as most of you are aware, you can buy an airflow measurement from an air monitor or whoever on the market and very easily integrate it into your power plant. With some of this advanced measurements that we're talking about with coal lines and burner airflow, the plants have never had these measurements before. So yeah, our air monitor stays very close to make sure that we work with the customer. We train all the operators so that they know what they're looking at. We train them with their data so that they can understand what it is that they're looking at. Okay, I think I'm back again.
Yeah, you're back again here. Let's see. Yeah, let's see.
You got it?
We're looking at the general burner test arrangement here, right?
Another important feature that we use when we're measuring flow, of course, we're using a pitot tube. So as with all of our pitot measurements, we have a transmitter that's looking at the DP and transmitting the signal back to the DCS to use for the mass flow measurement. These are purge valves. We also want to make sure that the pitot tubes stay clean. So as with everything we do, primary airflow, secondary airflow, overfire airflow, and burner airflow, there's a series of valves that are used to blow the pitot tubes back once a day. So there's a timer that goes off within the transmitter, or it can come from the DCS, tells this to do its purge. It locks and holds its signal to the DCS. It says it's in purge mode, and it shuttles the valves, which brings instrument air to each of the pitot tubes and cleans them out. So what do we do? As Bob said, you know, these are all new measurements. How does one know what to do? Again, we typically work with the power plant to help them develop new control room screens if we want to take it to this level. And what do I mean this level? Some people are buying coal flow measurement, as an example, just to solve milling problems or to prevent fires. But some people are doing complete air-to-fuel ratio control, which is what this presentation is really geared towards. So I've gone through two different technologies to show you that we can measure coal flow in each burner line, and we can measure secondary airflow in each burner. We can take and divide the airflow by the fuel flow and come up with an air-to-fuel ratio. Down here in the bottom, what we do, this is an opposed wall-fired unit, so we're looking at two wind boxes. We come up with an air-to-fuel ratio for the front wind box and one for the rear wind box. This is the average air-to-fuel ratio based upon all the mills that are in service. So if we have an average air-to-fuel ratio and all the burners operated at that average, we have good combustion. So that average becomes the set point. So on the front wall, for instance, we know how much fuel from the feeders and how much air from the secondary air duct is going to that wind box. We take, that becomes a set point. If this burner right here is running lower than that set point, it means it's not getting enough air. So its air register is going to open up until that air-to-fuel ratio is met. And what's the result? The result is now on the back end where you're measuring your excess O2, we're going to see a much flatter O2 curve. You're going to see much flatter O2. If you're measuring CO, you're going to see much less CO because you have good combustion at each and every one of these burners. So even if using coal valves, we couldn't balance this, say the FL4 and the FL5 burners. They're not perfectly balanced in terms of mass of coal. We use those air registers to very easily adjust them to bring the right air-to-fuel ratio to each burner. And on T-fired units, we do something very similar. But again, instead of using the pitot tube technology, we use static pressure measurement across each damper, aux air, fuel air, aux air, fuel air. So we measure the static pressure, and we convert that, again, using our wind tunnel out in Santa Rosa, California. We're able to develop curves that help us convert damper position and static pressure into a flow across each damper. So again, there's the static pressure measurement. This is our wind tunnel in California where we are mocking up a specific corner for a customer. And then we develop control room screens. Again, much like the wall-fired units, this is a corner-fired unit where we're measuring air-to-fuel ratio for each aux air and fuel air compartment. And again, the dampers can be modulated to give equal or biasing. If we want to run the bottom burners richer than the top burners, we don't need to be at that the set point for the average air-to-fuel ratio can become a fraction of it. So if we want to run the bottom burners instead of at the average air-to-fuel ratio, if we want to run them richer, we make it a 0.8 times the average. These are more examples of control room screens. Each plant has its own wants and needs as far as what do we want to see on a screen? What do we want to see when we develop a control room screen for our operators? And we work with the operations managers and with operators to develop these screens. We don't want to make them too busy. I realize some of these screens can look, we've got coal flow measurement, we've got velocity of the coal particles, we've got secondary airflow measurement, we've got the airflow register position, we've got, air to fuel ratios. We can put, a lot of people want to have the damper position, the secondary air damper position on this screen. We typically want to put the oxygen, the excess O2 grid on this screen so that an operator can see, they can look for burn, if they have a low or high O2, they can look and see, hey, do I happen to have an air-fuel ratio that's not being met? So again, we work with operators, and it's a continuing, Bob, it's a continuing and ongoing relationship that we have with our customers. Again, this is another control room screen of a mill and showing valve position and coal flow through each coal conduit. Finally, to end my presentation, I have about 10 slides from a presentation that was given by a customer of ours. This is Progress Energy, who has our equipment on plants throughout North and South Carolina as well as Florida. And this paper has been given by this particular utility at several power conferences, and it was also written into a paper that was put into Power Engineering magazine earlier this year. This power plant is a B&W opposed wall-fired unit, 770 megawatts with 6 MPS 89 mills. They have 54 DOB4Z burners, and they're compartmentalized burners. So each row of burners has its own wind box. The equipment that they added was coal flow measurement and coal valves for each coal pipe, burner secondary airflow measurement with a purge, burner secondary air adjustment. The burners that they bought from the OEM did not have a drive on them. They were manually adjustable, so they put damper drives on them. And they had an existing primary air system, which they kept. They just put an automatic purge system on it to make sure the integrity of it would be maintained. They had O2 probes. They moved them to an area they felt is more representation of good excess O2 as caused by the burners. And they also added CO measurement very close to the O2 probe so that they had an idea of what the CO was across the back end. So this presentation that they have made shows that their desire is to take unbalanced coal, to put in coal valves, and better balance the coal to each burner. Again, this is a depiction of their coal valves that they use, how they balance the data. You probably recognize I've used this earlier in this presentation. On the airflow side, this is what their wind boxes look like. They have, this is one wall, so we're looking at 3 wind boxes. The other wall has 3 more wind boxes. Each wind box has 9 burners in it. So we calibrated their burner in the wind tunnel in Santa Rosa so that they had curves so that they would know exactly what the mass flow of air was moving through each secondary air duct. And then the idea is to use the adjustability of the secondary air register of the burner and adjust their airflows accordingly. And the result was, in addition to the unit that they put us on, Unit 4, they have an identical unit, Unit 5. So the only thing different now between 4 and 5 was that Unit 4 got what they called the CCM, the Continuous Combustion Management System. Now this is the O2 grid on Unit 4 compared to Unit 5. We can see a much flatter O2 profile, and obviously I'm sure you note a lower O2. Because they're measuring CO, they know that since they turned the CCM on, the CO was removed. Now they're able to back off their O2. And by backing off their O2, they're improving plant efficiency and they're reducing thermal NOx. Unit 5, subsequent to this paper, has also gotten a CCM, so its O2 grid will no longer look like that. Again, they measure CO on the back end with a separate CO probe and an infrared CO monitor, which is also capable of measuring O2 if they desire, and they did desire. So what did they do? This was their O2 curve. before they added CCM, and this is their O2 curve after CCM was implemented. And these are their project results: 0.5% efficiency and improvement in efficiency, which has given them a couple $1 million a year in fuel savings, as well as a NOx reduction. Now, this particular plant has SCRs, so NOx was not a driver, but they did get NOx reduction, inlet to the SCR NOx reduction, which is going to help with ammonia consumption. They had a decrease in unburned carbon, which makes the red line being the sellable line. Unit 4 is the black curve. They can always remain sellable with their ash. And these are some soft benefits that the plant had as a result of implementing the CCM system. And that concludes my presentation.
We're ready now for questions from the floor. Who would like to start them off? Dave, you might just want to comment about the ramifications with all the new regulations on mercury and PM 2.5 and so forth. Really, when you take a plant like the one we were just looking here, they got a 0.5% increase in efficiency, but that really means it's a 0.5% decrease per megawatt hour in every one of these very difficult pollutants.
That's true, Bob. The other thing it's doing, a lot of power plants now that are coming to us that we're putting equipment on are trying to burn different fuels. So power plants that were burning great Central Appalachian coals are now being forced, because of high pricing, to burn Illinois Basin coals or Northern Appalachian coals. And to do that, they know that it's going to cause slagging problems in the furnaces, and it's going to cause all different types of problems. By better metering the coal flow to each burner, they're able to improve combustion and be able to burn coals like this. So some power plants that have come to us hoping to burn 20 or 30% Illinois Basin fuel blended with their good coal are finding they can burn 100% Illinois Basin fuel.
Gives them a lot more flexibility then.
A lot more fuel flexibility associated with it.
Yeah. Other questions?
I guess I'll point out also that this has been used, the coal flow measurement, for instance, has been used on every fuel type, every milling type, everybody's ball mill, ball tube mill, exhauster mills, pressurized mills. There's not one out there that we haven't installed this equipment on. It is not new anymore. We have a number, well over 100 full boilers that we've installed all this equipment on.
Yeah, that was a question.
I have a question. Hello?
Yes.
Yeah, I have a question. Yeah, you go out to retrofit a plant, and I realize this is going to be a rather broad question. What is the cost, let's say, for your full bore system to increase this efficiency in terms of, capital improvements in dollars per megawatt measurement?
Sure. Progress Energy, on the job that they presented, which, the last slides I ended with, they spent about $3 million on total installation costs. So, basic rule of thumb costs, it costs about, $9,000 to measure coal in each coal conduit. It costs $3,000 to $4,000 for a coal valve in each coal pipe. And then the airflow measurement costs roughly $7,000 to $8,000 for a low NOx burner, depending on which burner, to measure the coal. The controllability usually is already in that burner. Most of them already have drives on it. So now you've got all that hardware. Now you've got to install it. Typical cost might be 3/4 of the cost of the hardware is what it typically might cost to install it. And then lastly, you've got some control room screens and such you need to build. So again, giving you an example, with a 54 burner unit, costs about $3 million total to save roughly $2.5 million a year in fuel costs.
Yeah, almost recover the cost in about, let's say about 6 months then. So you're talking about $3 million over about, what was Progress, 770 megawatt unit?
Correct.
Okay. Thank you very much.
Yes.
Other questions?
Yes.
I had a question regarding the wear. I'm sorry to interrupt, good.
No, please.
I had a question regarding wear. You mentioned a plant that had Texas lignite, and they were wearing out pretty fast for microwave sensors.
Yes.
We got a similar ash. It's about 22% ash. I mean, what kind of wear time do you experience with these?
Well, what we've done in the past is we typically, we send sensors to customers who feel they might have a problem, like up in North Dakota or Saskatchewan. And so they put them in and they look for wear. Put them in for 3 months, 6 months, however long they feel. We've not seen. We have equipment installed in lignite from the Dakotas and lignite from Canada, and we've had no wear in 4 to 5 years that we've put sensors in.
Okay.
But Texas lignite was very fast. It wore out quicker than I would have expected.
That's kind of what I'm worried about. We're real high in silica, and like I say, we're about 22%. So, I mean, how much are you talking for a probe?
Well, I mean, we just send them out to you.
Okay.
Yeah, no, I mean, it's...
All right, good deal. Appreciate it.
Yes, sir.
Other questions?
Hey, Dave, on the fineness, do you if you're looking to measure fineness, you need to replace a section of the PA duct on the outlet of the mill?
Well, I really, I didn't fully explain fineness. I glossed over it, and to be honest with you, I only added these slides yesterday. We've been working on it for several years, but there's two different things we're working on. Because I say that slip is directly correlatable into fineness, we've built this device to very accurately measure the air and to measure the coal. Typically, we'd put it in one pipe out of a mill. I mean, again, we're assuming that the mill delivers the same fineness coal to each pipe, so we put it in one pipe. Now, the other thing that we can do is, well, Dave, if there's a relationship between slip and fineness, if I were to look at the primary air into a pulverizer and compare it to the average velocity, which we automatically, we calculate the average velocity on one of our screens in our SCADA system, why can't I convert that into slip? It's possible that we don't need to add any additional hardware if we have accurate primary airflow. So we're doing further testing on that. But right now, the device that I showed is a separate device, and typically it goes in one pipe out of each mill.
Okay.
And again, why are people doing this? What we want to be able to do, and we can do now, if somebody has our cold flow system, they can compare, they can look at the velocities, the average velocities on each mill, and pretty much infer, if one mill has very low velocities for the same mass flow, odds are its fineness is bad, and that's probably the next mill I'm going to want to service.
Yeah, absolutely. You could help start doing better predictive maintenance on your overhaul cycles because the fineness level's dropping.
Right.
Okay. Thank you.
Other questions?
This is John Guthrie from Paragon Air Heater. I just wanted to add something on that issue of the Texas lignite erosion. But generally what we see around the world actually is the erosive ash usually occurs when you've got a combined silica and alumina content in the ash at 85% or above. That is certainly the case with Texas lignite and a few other coals. But generally, high ash does not automatically mean high erosion. And the experience down with the lignite that you've had is similar to the experience with other components on the downstream side of the air heater. So I wouldn't be that concerned about high ash being a problem with erosion. It would be the silica and alumina content, which coincidentally also means high resistivity and ash for precipitators as well. Just wanted to add that.
Thank you, John.
Guys, we're actually also looking at really high velocities. We've got huge burners, and we're looking at a little less than 10,000 feet per minute. So, 150-some feet per second.
Yeah, I mean, there's no question about it that the higher your velocity, the faster you're going to erode anything, and it's exponential. Because we're on units that have converted from eastern coal to PRB coal in small diameter pipes, we have seen higher velocities in some cases, and it's a concern. We feel, you know, the product hasn't been installed that many years, that we maybe only have 4 or 5 years of service now, but I wouldn't expect to get 10 years of service out of sensors if we've got high silica, alumina, for instance, and a high velocity. There's no question it is a concern, and it's something that should be looked at. The sensors are easily, you know, it's very easy to take them out. They're threaded in and they come out. But I'm sure your maintenance group isn't going to want to hear them. They're going to have to be changing these things out too regularly.
Right.
So the only thing I would offer is we should look at it. We should take a mill that we know, for instance, has a high velocity output, or a pipe we know is prone to high velocity. Put a couple of sensors in. And see if there's erosion quickly. See if there's erosion in 3 months.
Okay, cool. Appreciate you guys' input.
Other questions? You mentioned the fuels. What about the biomass co-firing? Have you tackled that?
We've not. You know, people through the years have asked us about other, you know, even lime, you know, measuring pulverized lime. We've not used it for anything other than the pulverized coal, and I'm sure it's something would be open to test, but it's not been tested now.
Yeah, I guess they're basically two versions of that. One is, you know, separate burners where the biomass is pulverized and injected separately, and then secondly where you just add it to the conveyor belt going in with your coal feed. So. Yeah,
I mean, I'm pretty sure because the particles need to create an electrostatic signature, which is what we use to cross-correlate. And most things rubbing together in a coal pipe are going to do that. So measuring the velocity is I'm sure would be done. The next thing is that you need a dielectric coefficient that you know of to make sure that the microwave can read frequency in the proper ranges we need to measure. And so it's very easy to check if somebody were interested in measuring biomass or any other material. We just have been very busy there's a lot of coal-fired plants in North America that we've been tied up with.
Sure. Other questions? If not, I'd like to thank Dave for a very interesting presentation today. You will get access to the recording, and so if you missed anything, you can go back and listen to it again. So again, thanks for attending, and thank you again, Dave.
Thank you.
Bye now.